Tonight, we're going to travel to the edge of our solar system. Not the edge people usually talk about. The real one, 100,000 times farther from the sun than Earth is, in every direction, through frozen darkness that no spacecraft has ever entered. The solar system is not a small neighborhood of 8 planets orbiting a star. It is an enormous, layered structure stretching nearly halfway to the nearest star, and almost none of it has ever been explored. And what lies beyond the last planets isn't empty. Every layer outward is colder, darker, and more terrifying than the last. By the end of tonight, you're going to understand exactly how deep our solar system runs, what's actually out there in the dark, and why nothing we've ever built has come anywhere close to reaching it. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with where you are right now. You're on Earth, roughly 93 million miles from the Sun. That number has a name: 1 astronomical unit. It's the measuring stick astronomers use for distances inside the solar system. Learn that unit, because we're going to stretch it by a factor of 100,000 before we're done. The first thing outward from Earth is Mercury, at 0.4 astronomical units. It's the smallest planet in the solar system, barely larger than Earth's moon, and one of the strangest in terms of extremes. It has almost no atmosphere, which means nothing to distribute heat or hold it in. The side facing the sun reaches over 800 degrees Fahrenheit, while the night side drops to -290. A swing of over 1,000 degrees between one face and the other on the same planet at the same moment. Mercury also has a core that takes up roughly 85% of its radius, disproportionately large compared to any other planet in the solar system. The leading theory is that a massive early collision stripped away most of the outer layers, leaving the dense iron interior behind. The evidence fits, but it's still debated. Venus comes next at 0.7 astronomical units, and from a distance, it looks like Earth's twin, nearly identical in size, similar in mass, a comparable distance from the Sun. It is nothing like Earth. The atmosphere is almost entirely carbon dioxide, and 90 times denser than ours, producing a greenhouse effect so extreme that the surface averages around 900 degrees Fahrenheit, hotter than Mercury, despite being twice as far from the Sun. The pressure at ground level is equivalent to being nearly a mile underwater, and every spacecraft ever sent to the Venusian surface has been destroyed within hours of arrival. Venus also rotates backward compared to every other planet, and so slowly that a single day there is longer than its year. The reasons for both of those things are still not fully understood. Then, the inner solar system thins out. Mars sits at 1.5 astronomical units. The last rocky planet, before the solar system, opens into something much larger. It's about half the diameter of Earth, with a third of the surface gravity and less than 1% of the atmospheric pressure, cold and thin and inhospitable by any measure. But it wasn't always. Ancient riverbeds cut across the surface. Dried lake basins hold mineral deposits that only form in the presence of liquid water. Mars was wet once, and warm enough to sustain it. Something changed. The magnetic field weakened. The atmosphere bled into space. The water froze or escaped, and the timeline of exactly how and when is still being pieced together. What's left is a planet with the largest volcano in the solar system, Olympus Mons, nearly 14 miles high, and a canyon system, Valles Marineris, wide enough to span the continental United States. a world that clearly had more going on than it does now. Mars is also the most likely destination for a human crew beyond the Moon, and what that journey involves is its own story. For now, it's the last landmark before the solar system changes character entirely. Past Mars, the inner solar system gives way to the asteroid belt, and beyond that, everything scales up by an order of magnitude. This is where popular culture has been systematically misleading people for decades. In films, the asteroid belt is a chaotic, churning wall of boulders that pilots weave through at high speed, rocks bouncing off the hull while dramatic music plays. The reality is different enough to be almost funny. The asteroid belt contains over 1 million objects larger than about 3,000 feet across, and millions more smaller than that. It also spans an enormous volume, a broad, donut-shaped region extending from roughly 2 to 3.5 astronomical units from the Sun. When you distribute even 1 million objects across that much space, the average distance between any two of them is around 600,000 miles. That's nearly 3 times the distance from Earth to the Moon. If you flew through the asteroid belt on a straight trajectory with no attempt at navigation, the statistical probability of coming within 1 million miles of anything is already very low. You could fly through it in a straight line, eyes closed, and most likely never come anywhere near a rock. The belt is quiet, sparse. The asteroids out here are mostly rocks and metals, silicates, iron-nickel alloys, carbonaceous material, the remnants of solar system formation 4.5 billion years ago. Objects that never managed to coalesce into a planet, predominantly because Jupiter's gravity kept stirring up the region, preventing the scattered material from ever settling into stable accumulation patterns long enough to build something larger. The total mass of everything in the asteroid belt combined is less than 4% of the mass of the Moon. It's not the building material of a lost planet. It's the material that never became one. Some asteroids are nearly spherical, large enough that their own gravity has pulled them into rough balls. The largest, Ceres, is about 590 miles across. When the Dawn spacecraft arrived at Ceres in 2015, it found a world with a surprisingly active geological history. Bright spots, visible from Earth through telescopes, turned out to be deposits of sodium carbonate salt minerals brought to the surface by briny water moving up from a subsurface reservoir. Ceres appears to have had, and may still have, pockets of liquid brine somewhere beneath its surface. An asteroid belt object with subsurface liquid. The solar system does not offer simple dead places. Other asteroids are tumbling, irregular chunks shaped like elongated peanuts, rotating in the dark. Bennu, which the OSIRIS-REx mission studied in detail and returned samples from in 2023, is a rubble pile, a loosely bound collection of fragments held together by gravity and van der Waals forces, rather than a coherent solid rock. Walk on it too fast, and you'd drift off its surface and into space. The sample returned from Bennu contained carbon-rich material, amino acids, and hydrated silicate minerals, evidence that water-altered chemistry happened on this small body. The asteroid belt is a collection of time capsules, each one preserving different information about conditions at different locations in the early solar system. At this distance, the sun still blazes. The solar wind streams outward. The heliosphere is intact in every direction. The giant planets are still ahead, and the distances between them dwarf anything in the inner solar system. Jupiter alone is 5 times farther from the Sun than Earth is. Saturn is more than twice as far again. Beyond the asteroid belt lies the domain of the giant planets. Jupiter is first. Nothing you've seen from Earth, not photographs, not simulations, not the view, through even the most powerful amateur telescope, prepares you for Jupiter at close range. At 5.2 astronomical units from the Sun, it's the most massive object in the solar system, other than the Sun itself. To grasp what that actually means, Jupiter contains more mass than all the other planets, moons, asteroids, and comets in the solar system combined, and then some, more than twice over. You could add up everything in the solar system, except the Sun and Jupiter, double that mass, and you'd still have less than Jupiter. The planet is big enough to contain more than 1,300 Earths by volume, and from the right distance, it announces itself. The iconic banded appearance, swirling brown and orange and white stripes, visible from Earth through even a modest telescope, resolves at close range into something extraordinary. These aren't thin cloud stripes painted on a sphere. They're weather systems extending thousands of miles in depth, atmospheric streams moving at hundreds of miles per hour, with the boundaries between adjacent bands being zones of intense wind shear, where streams moving in opposite directions generate turbulence, on a scale that would reduce any structure humanity has built to fragments. Thunderstorms on Jupiter routinely release energy thousands of times greater than the most powerful lightning ever recorded on Earth. Individual storm systems can persist for years without dissipating. The Great Red Spot is the most famous feature of any planet in the solar system. It's been continuously observed since at least the late 17th century, over 350 years of recorded observation, and may be considerably older. It's a high-pressure anticyclone, a storm rotating counterclockwise in Jupiter's southern hemisphere, wider than the entire planet Earth at its historical peak. It has been shrinking in recent decades. From roughly 25,000 miles across at its historical maximum to closer to 10,000 miles in recent measurements. Nobody knows exactly why. Whether this shrinkage reflects a temporary oscillation in storm dynamics or a long-term trend toward eventual dissipation is genuinely uncertain. The oldest, continuously observed feature on any planet in the solar system might be in its final centuries. Jupiter's magnetic field is the most powerful of any planet, roughly 20,000 times stronger than Earth's. Its magnetosphere, the region of space dominated by Jupiter's magnetic influence rather than the Sun's, extends so far outward that if you could see its boundaries from Earth with the naked eye, they would appear about 5 times the diameter of the full moon in the sky. Inside that magnetosphere, trapped particles accelerated to enormous energies form radiation belts intense enough to damage sophisticated electronics and dangerous to a human being, without serious shielding, even inside a parting spacecraft. The Galilean moons, Io, Europa, Ganymede, Callisto, orbit in and around this radiation environment. Io is the most volcanically active body anywhere in the solar system. Jupiter's tidal forces continuously squeeze and flex Io's interior. The friction generates so much internal heat that hundreds of active volcanoes continuously resurface the moon. Sulfur dioxide plumes blast hundreds of miles into space from the most energetic vents. Lava lakes pool in the calderas of shield volcanoes. Io has essentially no impact craters. Eruption rates bury them faster than they can accumulate. The surface you see is not the surface from last month. Europa, the next moon out, is one of the most scientifically important objects in the solar system. Beneath its cracked and ridged icy surface lies a global ocean of liquid water. The evidence for this comes from multiple independent directions. Tidal heating from Jupiter and the orbital resonances among the Galilean moons generates sufficient energy to maintain a liquid ocean despite Europa's distance from the Sun. Magnetic induction measurements from the Galileo spacecraft show a conducting layer beneath the ice, consistent with a salty, liquid ocean. The surface geology shows crossing fractures, chaos terrain where the ice has been disrupted from below and refrozen, and regions where fresh material has apparently been brought up from below, all consistent with a floating ice shell above liquid water. That ocean is estimated to be 60 to perhaps 100 miles deep. It contains more liquid water than all of Earth's oceans combined. Whether anything lives in it is one of the most consequential open questions in the history of science. The Europa Clipper spacecraft, launched in October 2024, is currently traveling toward Jupiter to answer that question, or at least to characterize how answerable it actually is. It will make dozens of close flybys of Europa, building up detailed maps of the ice shell's structure, the ocean's chemistry, the plumes that appear to intermittently erupt from the surface. What it finds will shape the direction of astrobiology for a generation. Ganymede, the largest moon in the solar system, is bigger than the planet Mercury. It's the only moon known to generate its own magnetic field internally. It also likely harbors a subsurface ocean sandwiched between layers of ice, based on magnetic induction data. Callisto, the outermost of the four large moons, has one of the most heavily cratered surfaces in the solar system, a geological record largely undisturbed for billions of years, because Callisto has little internal heat to drive resurfacing. And Callisto also shows magnetic induction signatures consistent with a subsurface conducting layer. 3 of Jupiter's 4 major moons may harbor liquid water in their interiors. 3 separate candidates for habitable environments, all in one planetary system, each one worthy of its own dedicated mission, each one an argument for spending decades here. Saturn sits at 9.5 astronomical units from the Sun. The rings announce it before anything else. Even from millions of miles away, they transform Saturn's appearance into something without a clear visual analogy in ordinary experience. A flat, gleaming disk spanning hundreds of thousands of miles in diameter, and yet only a few hundred feet thick through most of its extent. The horizontal reach is enormous. The main visible rings span from just a few thousand miles above Saturn's cloud tops out to nearly 50,000 miles above them. The vertical extent through most of the rings is a few hundred feet. Some parts may be as thin as a few dozen feet. If you scaled the rings so their width matched the width of a standard sheet of paper, the paper would be several times thicker than the rings are in proportion to their span. Geometry doesn't have many features that extreme. The rings are made mostly of water-ice particles ranging from microscopic dust grains to chunks the size of a house, with a small proportion of rocky material and organic compounds mixed in. When sunlight catches them at the right angle, they blaze, brighter than the planet itself. From the night side of Saturn, looking back toward the Sun through the rings, they become nearly transparent, and stars are visible through them. That same structure looks completely different depending on where you are and where the light is coming from. The internal architecture of the rings is extraordinary. The Cassini spacecraft spent 13 years in Saturn's orbit, from 2004 to 2017, and returned more information about the ring structure than all previous observations combined. Thousands of individual ringlets and gaps, each shaped by gravitational resonances with Saturn's moons. The Cassini division, the prominent dark gap between the A and B rings, is maintained by a resonance with Mimas. Objects in the Cassini division orbit Saturn in exactly half the time it takes Mimas to complete an orbit, which means they receive a consistent gravitational tug in the same direction every 2 orbits. Over millions of years, those tugs cleared most of the material out of that zone. But the Cassini division isn't truly empty. It still contains material, just less of it. Propeller-shaped structures, embedded within the rings, mark the locations of small moonlets, perhaps a mile across, that carve gaps in the ring material but are too small to clear their entire orbital path. Spiral density waves propagate through the rings from the locations of orbital resonances with larger moons, like ripples moving through a pond, visible in the ring structure for thousands of miles outward from their origin points. Cassini also found that the rings are geologically young. Analysis of ring mass and the rate at which particles fall into Saturn's atmosphere points to a formation date somewhere between 10 million and a few 100 million years ago. When early dinosaurs first appeared on Earth, Saturn's current ring system may not yet have existed. They'll be gone in another 100 million years or so as ring particles continue spiraling inward. We're watching Saturn during what is, geologically speaking, a brief window of exceptional beauty. Titan is Saturn's largest moon and one of the strangest places in the solar system. It has an atmosphere, not a thin wisp like Mars. A thick, hazy nitrogen atmosphere, denser than Earth's, producing a surface pressure about 1.5 times what you experience at sea level. The surface temperature averages around -290 degrees Fahrenheit. At that temperature, methane behaves the way water behaves on Earth. Titan has a complete methane cycle. Methane evaporates from surface liquids. It forms clouds in the thick orange haze. It rains down slowly through the dense atmosphere, in large drops falling through lower gravity than Earth onto the surface. It flows in rivers that have carved valleys, visible in radar imagery. It collects in lakes and seas in the polar regions. The Ligaea Mare, one of Titan's northern seas, spans hundreds of miles and contains a volume of liquid methane and ethane, estimated at some 55 times the liquid water in all of Lake Michigan. The Huygens probe parachuted through Titan's atmosphere on January 14, 2005, and during its descent imaged a landscape that looked, in the radar imagery, unmistakably like river delta systems. When it landed on the surface, it found rounded pebbles smoothed by flow. Titan has active weather, active rivers, active seas, not of water, but of liquid methane and ethane. Complex organic chemistry operates continuously on Titan. Ultraviolet radiation from the sun breaks apart methane and nitrogen molecules in the upper atmosphere. The fragments reassemble into a complex family of organic compounds called tholins, reddish-orange polymeric molecules that give Titan its characteristic hazy color. Tholins rain slowly down through the atmosphere and coat the surface in a thin layer. Some of those tholins include precursors to amino acids and nuclear bases. The chemistry that leads to biology on Earth is being manufactured on Titan in a different solvent system, in the dark, right now. Saturn's moon Enceladus delivers an entirely different kind of revelation. It's small, about 300 miles across, smaller than the state of Arizona, and it's erupting. Geysers of water vapor, ice particles, and organic compounds blast from 4 parallel fractures. Near the South Pole, features named the Tiger Stripes at over 1,000 miles per hour. The material escapes Enceladus's weak gravity and feeds Saturn's E-ring from the outside. When Cassini flew through those plumes during dozens of close passes, its instruments found water, molecular hydrogen, carbon dioxide, methane. Complex organic molecules, including amino acid precursors and silica nanoparticles of a type that form only when liquid water at elevated temperatures contacts rock, the signature of hydrothermal activity. On Earth, hydrothermal vents on the seafloor support ecosystems built entirely on chemical energy rather than sunlight. Bacteria, archaea, tube worms, shrimp, fish, entire food chains, never connected to photosynthesis. Enceladus has the conditions for similar chemistry. Inside a tiny world, at Saturn's distance from the Sun, in a region of space where temperatures on the surface reach -330 degrees Fahrenheit. If you were designing a body to have subsurface liquid water, Enceladus is not what you'd design. And yet, there it is. The planetary solar system has already handed you more habitable candidate environments than the most optimistic scientists of 50 years ago would have predicted. Saturn recedes. Uranus orbits at around 19 astronomical units. At that distance, the Sun has dimmed significantly. It's still a brilliant point, dramatically brighter than anything else in the sky, but it no longer dominates the way it does in the inner solar system. The character of the light has shifted. Uranus is a pale blue-green disk, smooth and featureless in visible light compared to Jupiter or Saturn. Its most dramatic characteristic isn't visible at all. It's the axial tilt. Uranus is tilted 98 degrees. It rotates on its side. Not slightly tilted the way Earth is, at 23.5 degrees. Sideways. The North Pole points almost directly at the Sun during the northern summer solstice. For 42 years of its 84-year orbit, the North Pole bakes in continuous sunlight, while the South Pole sits in total darkness. Then, the situation reverses. The equatorial regions see rapid day-night cycles only near the equinoxes, when neither pole faces the Sun. The cause of this is almost certainly an ancient collision. Something with mass roughly comparable to Earth or larger struck Uranus at a steep angle during the violent early history of the solar system and knocked it over. Simulations of how such a collision would have played out and what it would have done to Uranus's internal structure, its moons, and the surrounding debris are still being worked through. Some models suggest a single, large impactor. Others suggest multiple smaller collisions. Uranus has 13 known rings, narrow and dark. Discovered in 1977, when astronomers watching it occult, a background star noticed symmetric dimming events before and after. The star flickered on one side, then the other. Symmetric occultation, events around a planet mean rings. 27 known moons, all named for characters from Shakespeare's plays and Alexander Pope's The Rape of the Lock. Miranda, one of the smaller inner moons, has a feature called Verona Rupes, a cliff estimated at between 6 and 12 miles high, the tallest known cliff face in the solar system. Miranda's geology is jumbled in a way that doesn't fit easily into standard models of how icy moon surfaces form. Terrain types that shouldn't be adjacent to each other sit side by side. Some researchers have suggested this reflects disruption and reassembly, the moon being broken apart by an ancient impact and pulling itself back together under gravity in a disordered way. At Uranus distances, the Sun delivers about 1/370th the energy it delivers at Earth. Solar power as a primary energy source is not practical. For any spacecraft operating here, nuclear power is the only option. The thermal environment is already severe temperatures in the deep negative hundreds of degrees Fahrenheit. And you're not even 2/3 of the way to Neptune. A tiny fraction of the way to the Oort cloud. Neptune orbits at 30 astronomical units from the Sun. Discovered in 1846 through calculation before observation. Anomalies in Uranus's orbital motion accumulated over decades of careful measurement. They pointed to a gravitational perturber, something unseen, pulling Uranus slightly off its predicted path. Two mathematicians independently calculated where that object had to be. Urbain Le Verrier's calculation was the one acted on first, and when Johann Galle pointed a telescope at the predicted position on the night of September 23, 1846, he found Neptune within a degree of where the math said it would be. A planet discovered through pure mathematics, before anyone had ever seen it through a telescope. One of the great demonstrations of predictive science in history. Neptune is an intense electric blue, the most deeply saturated blue of any planet we know of. Its atmosphere contains traces of methane that absorb red light and reflect blue. But something else, not yet fully characterized, contributes to the depth of color beyond what methane alone would produce. Neptune's atmosphere is among the most violent in the solar system. Winds reaching 1,200 miles per hour in some jet streams, making it the planet with the most extreme atmospheric wind speeds we know of. And Neptune receives the least solar energy of any planet. What drives those winds, with so little energy input, is internal heat. Neptune radiates about 2.5 times more energy than it receives from the Sun. Residual heat from gravitational contraction during formation, 4.5 billion years ago, slowly leaking outward. It's still warm inside. Uranus, nearly identical in size and composition to Neptune, radiates almost no excess heat. Its atmosphere is relatively calm compared to Neptune's. Two similar worlds. One energetically active, one sluggish. The reason for the difference is still not fully understood. Neptune has been visited by exactly one spacecraft in history. Voyager 2, launched in 1977, flew past in August 1989 after 12 years of travel. The flyby lasted a matter of days. The images and data from those few days of closest approach remain the primary source of close-up information about Neptune. We have not sent an orbiter. We haven't gone back. A world we've observed in detail for a few days out of all of human history. Neptune's largest moon, Triton, is one of the most geologically unusual objects in the solar system. It orbits Neptune in the wrong direction. Every large moon in the solar system orbits in the same direction as its planet's rotation, because they formed from the same rotating disk of material that formed the planet. Triton orbits retrograde backward. This means Triton wasn't born here. It was captured from somewhere else. Almost certainly from the Kuiper Belt, billions of years ago. The capture process was violent and dynamically complex. Triton's original orbit was wildly elliptical. A capture orbit always is, and tidal interactions with Neptune over time circularized it. That process released enormous energy in Triton's interior through tidal heating. Despite all that, Triton is still active. Voyager 2's cameras detected geysers near the South Pole. Not water, nitrogen gas and dark material, erupting upward through the thin nitrogen atmosphere. Solar heating warms dark patches of nitrogen ice just below the surface. The nitrogen sublimes goes directly from solid to gas and the pressure blasts material upward in dark plumes that stream downwind and settle on the surface in dark streaks. A captured moon with active geysers. Triton is also slowly spiraling inward toward Neptune, because its retrograde orbit means tidal drag is steadily sapping its orbital energy, rather than adding to it the way it adds to the orbital energy of moons orbiting in the right direction. In about 3.5 billion years, Triton will cross the Roche, limit the distance at which Neptune's tidal forces exceed Triton's own self-gravity, and be torn apart. Neptune will gain a spectacular ring system, one almost certainly more dramatic than Saturn's current rings. The outcome is written in the orbital mechanics, deterministic from the moment of capture. From Neptune's orbit, the Sun is a brilliant point source. No disk visible to the naked eye without optical aid. The solar wind, stretched thin across a sphere 30 astronomical units in radius, is weak. The heliosphere's boundary is still far ahead. And the planetary solar system ends here. The deep outer solar system begins. Beyond Neptune, most people think the solar system ends. It doesn't. What lies beyond is a region extending so much farther than the entire planetary solar system that Mercury to Neptune look like a small cluster near the center of a vastly larger structure. The Kuiper belt begins around 30 astronomical units and extends out to roughly 50. It's a broad disk of icy bodies in the plane of the solar system, the frozen remnants of solar system formation, things that formed out there and never fell inward to become part of a planet. They've been sitting there for 4.5 billion years, cold and dark and largely undisturbed. Pluto lives here, at an average distance of about 39 astronomical units. For most of the 20th century, Pluto was the only known large object in the outer solar system beyond Neptune. It was discovered in 1930 by Clyde Tombaugh during a systematic photographic survey, and for 76 years it was classified as a planet, the 9th planet. The problem was that Pluto turned out not to be alone. When the Kuiper belt began to be systematically surveyed in the 1990s and 2000s, other large objects started showing up. The category of 9th planet started looking increasingly arbitrary. In 2015, New Horizons flew past Pluto after 9.5 years of travel from Earth. What it found there was almost nothing like what people expected. Pluto was supposed to be geologically dead, a frozen, ancient, cratered ball of ice sitting inertly in the outer darkness. Instead, New Horizons found a world with active geology. Mountains of water ice rising 3 miles above the surrounding terrain. The Tombau Regio, a vast heart-shaped basin spanning roughly 1,000 miles covered in nitrogen ice so geologically young that almost no impact craters mar its surface. Convection cells in the nitrogen ice, driven by heat from radioactive decay in Pluto's rocky core, slowly overturn the material like a lava lamp in slow motion. Possible cryovolcanoes, structures that erupt mixtures of water, ammonia, and other volatiles, rather than silicate lava rising from the surface. A thin atmosphere of nitrogen, methane, and carbon monoxide that thickens when Pluto is closer to the Sun and freezes out, snowing onto the surface. When Pluto swings to the far end of its 248-year orbit, Pluto generates enough internal heat from the radioactive decay of uranium, thorium, and potassium in its rocky core to maintain meaningful geological activity at temperatures of -370 degrees Fahrenheit. It's cold enough that most things we consider warm would be lethal there instantly. and it still has an active interior. Eris was discovered in 2005. It's about the same size as Pluto. The two are remarkably similar in diameter, but more massive. Its discovery is what forced the definitional question. If Pluto is a planet, what is Eris? If Eris is a planet, there would likely be dozens more large Kuiper Belt objects discovered in the coming years. The International Astronomical Union voted in 2006 to create a new category, dwarf planet, and reclassify Pluto accordingly. The category is scientifically sensible. Emotionally, it still apparently upsets a lot of people. The solar system has other dwarf planets out here. Haumea rotates so rapidly, completing a full spin every 4 hours, that centrifugal force has distorted it into an elongated ellipsoid, wider at the equator than at the poles, shaped somewhat like a flattened football. Haumea has 2 small moons, and it has a ring discovered in 2017, a ring around a Kuiper Belt dwarf planet. Quaoar has a ring too, announced in 2023. Its ring sits at a distance beyond where ring stability models suggested rings could exist, because at that distance, tidal forces from Quaoar should cause any ring material to quickly clump together. They haven't clumped. The models are incomplete. Makemake has a small dark moon discovered in 2016, visible only because it happened to be positioned in front of the dark sky during a Hubble observation, rather than in front of the bright body of Makemake itself. In 2019, New Horizons flew past Arakoth, a contact binary sitting more than 4 billion miles from the Sun. 2 lobes, about 9 miles and 13 miles across, gently pressed together at a narrow neck. Its surface is covered in pristine reddish tholins, unchanged since the solar system's formation 4.5 billion years ago. Arakoth formed when 2 separate small bodies in the early solar nebula slowly spiraled toward each other through gas drag and gently merged. No violent collision, no catastrophic disruption. Just a slow, gentle coming together, preserved intact in the cold ever since. A fossil of the solar system's first formation steps. And then there's Sedna, found in 2003. An orbit that stretches from 76 astronomical units at its closest approach to the Sun, already well beyond Neptune, out to roughly 940 astronomical units at its farthest. Its orbital period is approximately 11,000 years. At its current position, it's somewhere in the middle of that orbit, about 83 astronomical units out. Sedna's orbit doesn't make sense under any standard model of solar system dynamics. The Kuiper Belt objects cluster in the range of 30 to 50 astronomical units. The Oort cloud begins around 2,000 astronomical units and was thought to be shaped by distant stellar perturbations. Sedna's orbit spans from well beyond the Kuiper Belt to nowhere near the Oort cloud. It's in a region that wasn't supposed to have anything in it. Something created that orbit. The candidates are a passing star that perturbed the outer solar system billions of years ago, tidal effects from the Sun's birth cluster of stars, or an as-yet undetected massive planet. Several other objects with similar extreme orbits have since been found Sedna-like bodies with perihelia well beyond the classical Kuiper Belt. Their orbital orientations aren't random. They cluster. They point in similar directions. In 2016, astronomers Konstantin Batygin and Mike Brown published an analysis arguing that the most natural explanation for this clustering is the gravitational influence of an undiscovered planet. Not a small one. something between 5 and 10 times the mass of Earth, orbiting somewhere between 400 and 800 astronomical units from the Sun. Moving so slowly, a full orbit, taking 10,000 to 20,000 years, that current wide-field sky surveys haven't picked it up against the background of stars. The search is ongoing. No confirmed detection yet. Other explanations for the clustering have been proposed. Observational selection effects have been invoked. The evidence is debated. But the analysis is serious, conducted by serious scientists, published in a serious journal. There may be a planet in our solar system, a planet between 5 and 10 times Earth's mass that humanity has never seen. An undiscovered world in our own solar system, orbiting in the dark at 400 astronomical units while we've been cataloguing galaxies billions of light-years away. The outer solar system is still being explored. Its inventory is far from complete. At some distance between 80 and 100 astronomical units from the Sun, the environment undergoes a fundamental change. The solar wind has been flowing outward from the Sun since it formed. It's a continuous stream. Electrons, protons, helium nuclei, trace amounts of heavier ions blown off the Sun's corona and streaming radially outward at roughly 200 to 500 miles per second, carrying the Sun's magnetic field with it like a vast, spinning web. This outflow defines the heliosphere, the bubble of solar influence that the Sun maintains around itself. As the solar wind expands outward, it dilutes. Its density drops. Its pressure drops. The magnetic field it carries spreads across an ever larger surface area. And at some distance, the outward pressure of the expanding solar wind meets the inward pressure of the interstellar medium, the thin gas and dust between the stars, which has its own thermal pressure and magnetic field. Where those pressures balance, the solar wind is abruptly slowed from supersonic to subsonic speeds. This boundary is called the termination shock. It's not a surface in the way a planet's atmosphere has a surface. It's a region where the physics of the solar wind changes character sharply, where particles slow, temperatures spike, and the magnetic field becomes more compressed and tangled. The Voyager probes crossed the termination shock. Voyager 1 crossed it in 2004 at about 94 astronomical units. Voyager 2 crossed it in 2007 at about 84 astronomical units. Different distances in different directions. This asymmetry reflects the heliosphere's shape. The Sun moves through the interstellar medium at about 52,000 miles per hour, and this motion compresses the heliosphere on the leading side, pushing the termination shock closer. The heliosphere is not a sphere. It's more like a comet, shaped round on the side, facing the direction of motion through the galaxy, and extended into a long tail on the opposite side. Beyond the termination shock lies the heliosheath, a broad, turbulent region where solar particles that have been slowed and heated at the shock intermingle with particles from the interstellar medium. The heliosheath is complex. Early models imagined it as a relatively simple transition zone. The Voyager data, as the probes traveled through it, revealed something more intricate. The Sun reverses its global magnetic polarity every 11 years with the solar cycle. Each polarity reversal propagates outward with the solar wind, creating alternating regions of opposite magnetic field orientation in the heliosheath. At the boundaries between these regions, magnetic reconnection occurs. Field lines of opposite polarity snap together and release energy. This creates a foamy, bubbly structure in the heliosheath. a texture of magnetic reconnection events and closed magnetic loops threading through the region. Particles can be temporarily trapped in these magnetic structures. The heliosheath turned out to be more interesting than anyone expected. The data from it is still being analyzed. At the outer edge of the heliosheath is the heliopause, the boundary where the solar wind stops entirely and the interstellar medium takes over completely. The sun's particle wind yields to the rest of the galaxy. The heliopause sits at roughly 100 to 125 astronomical units from the sun, about 11 to 12 billion miles. At the crossing, the change is sharp. Solar wind particle density drops abruptly. The magnetic field shifts orientation. The interstellar magnetic field runs at a different angle to the heliospheric field, and at the boundary, the interstellar structure becomes dominant. Galactic cosmic rays, which the heliospheric magnetic field had been partially deflecting, flood in at their full, unmodified intensity. Nothing in the local environment beyond this point belongs to the sun. The interstellar medium fills the space. The thin gas between the stars, predominantly hydrogen and helium, with trace amounts of heavier elements, flows around and past the heliosphere. The local interstellar medium, the solar system currently occupies, is a relatively low-density region, sometimes called the local bubble. This bubble, roughly 1,000 light-years across, was carved out by supernova explosions over the past few tens of millions of years. The solar system is currently inside it, drifting through gas that is thinner and hotter than the average interstellar medium elsewhere in the galaxy. At some point in the future, or possibly in the past, the solar system was, or will be, in a denser region. When it is, the heliosphere shrinks. The protection it provides from galactic cosmic rays is reduced. The interstellar environment just outside the heliopause is not static. It changes on the timescales of the solar system's orbit around the galaxy. Its pressure is what the solar wind pushes against. Its properties, density, temperature, magnetic field orientation, determine the heliosphere's shape and location. What lies beyond the heliopause is interstellar space in the particle sense. But in the gravitational sense, you're still deeply inside the solar system. The heliopause and the solar system boundary are not the same thing. Not even close. What the heliopause does represent is the outermost edge of the sun's direct physical influence in the sense of particles and fields. Beyond it, no solar wind particle flows. The magnetic field structure changes completely. The particle environment is galactic rather than solar. A spacecraft sitting just inside the heliopause and one sitting just outside it inhabit physically different environments, even though both are in the same gravitational territory. The crossing is real and meaningful. It just isn't the edge of the solar system. The solar wind has limits. The sun's gravity does not. The solar system, defined by the reach of the sun's gravity, extends enormously farther. When spacecraft cross the heliopause, some coverage frames it as leaving the solar system entirely. It isn't. It's the edge of the solar wind, the bubble of charged particles the sun continuously blows outward into space. The outer edge of any star's gravitational domain is set by where its gravity becomes comparable to the gravity of neighboring stars and the background gravitational field of the galaxy itself. For the sun, that boundary is measured in light years. The structure at that boundary is the Oort cloud. It is a vast, spherical shell of icy bodies surrounding the entire solar system in every direction above, below, and all around. not confined to the disk of the planets, but extending outward into a complete sphere. The inner edge of the Oort cloud is thought to begin at roughly 2,000 astronomical units from the Sun. The heliopause sits at roughly 100 to 125 astronomical units. The Oort cloud's inner edge is 16 times farther out than the heliopause. The outer edge of the Oort cloud extends to perhaps 100,000 astronomical units, somewhere between 1.5 and 2 light-years from the Sun, depending on the model. Proxima Centauri, the closest known star to the Sun, is about 4.24 light-years away. The outer Oort cloud extends between 1/3 and halfway to the nearest star. The solar system is nearly as large as the gap between stars. The Oort cloud contains an estimated 2 trillion individual objects. 2 trillion icy bodies, ranging from small rocks to objects tens of miles across, distributed across a volume so enormous that the average distance between any 2 neighboring objects is tens of millions of miles. The Oort cloud is thought to divide into 2 broad zones. The outer Oort cloud, from roughly 20,000 to 100,000 astronomical units, is a nearly spherical shell. Its shape maintained by gravitational perturbations from passing stars and the galactic tide that randomize orbital orientations over billions of years. The inner Oort cloud, sometimes called the Hills cloud, sits from roughly 2,000 to 20,000 astronomical units and is thought to be more disk-shaped, closer to the plane of the solar system, and less perturbed by outside influences. It's also thought to be denser than the outer Oort cloud and may contain far more objects. It is functionally invisible. No telescope has directly imaged a single Oort cloud object. The density of material is so low that even passing through the inner Oort cloud would be imperceptible without specialized instruments. We know it's there because of what falls out of it. When a star drifts close to the solar system, which happens on timescales of tens to hundreds of thousands of years, as nearby stars move through the galaxy, its gravity perturbs the outermost Oort cloud objects. Some get nudged onto new trajectories that send them falling inward. They fall for thousands of years, accelerating steadily. When they finally reach the inner solar system, solar heating sublimates the surface ice's solid directly to gas, bypassing liquid at the low pressures of space. The outgassing streams backward in the solar wind. Dust, entrained in the gas, forms a second tail, curving gently along the object's orbit. We see a comet. Bright enough, sometimes to be visible in daylight. That comet is a piece of 4.5 billion-year-old material from the outermost reservoir of the solar system, knocked loose and falling inward for millennia before briefly lighting up the inner solar system. When it swings around the Sun and heads back out, it's returning to where it came from. The journey back takes thousands more years. The comet visible for a few weeks is the brief, lit portion of an orbit that spans all of recorded human history several times over. Think about what that means for a moment. The light from that comet's tail reaches telescopes on Earth, gets photographed, goes viral on the internet, makes the news. And the object creating it has been falling through the dark for longer than civilization has existed. It will be falling back outward, returning to the silence, long after whatever comes after civilization. The galactic tide also acts on the Oort cloud. The net gravitational pull of all the mass in the Milky Way stars, gas, dust, dark matter, creates a tidal force that is significant at the distances of the outer Oort cloud. This tidal force gradually alters orbital orientations over millions of years, nudging some objects into trajectories that eventually carry them inward. The galaxy reaches into the outermost boundary of the solar system and stirs it. The comets that appear in Earth's sky are partly products of galactic dynamics that have been operating for billions of years. Dense interstellar molecular clouds, concentrations of gas and dust that the solar system occasionally drifts through on its orbit around the galactic center, can also significantly disturb the Oort cloud. These encounters may trigger periods of elevated comet flux into the inner solar system. Some researchers have proposed connections between such events and mass extinction events in Earth's geological record. The causal chain is long and the evidence indirect, but the mechanism is real. The dynamics at the outer boundary of our solar system are connected across hundreds of millions of years to the history of life on this planet. The Oort cloud is not just a reservoir of comets. It's the outer wall of the solar system, shaped by the galaxy, and its dynamics are woven into the story of Earth itself. Now, consider where that leaves you. The outer edge of the Oort cloud, the true boundary of the solar system, sits at 100,000 astronomical units, 9.3 trillion miles, 1.5 to 2 light-years from the Sun. That is where the solar system ends, not at Neptune, not at the heliopause. Out there, at the edge of the gravity well, there's a moment that happens when you absorb that number properly. When you stop reciting it and start trying to feel the actual geometry of it. The Sun's empire, the territory it governs, the space within which any object is fundamentally a solar system object rather than an interstellar one, is nearly 2 light-years across. It contains Neptune, 30 astronomical units out. It contains the heliopause, 100 to 125 astronomical units out. It contains all of the Kuiper belt. It contains the vast empty expanse between the Kuiper belt and the Oort cloud. And it contains 2 trillion icy worlds at the edge, sitting in the dark, moving slowly, preserving the chemistry of 4.5 billion years ago. All of that is one solar system, ours. And the question that follows immediately from understanding that is, what would it actually take to get there? The fastest sustained cruise speed ever achieved on an outer solar system mission is roughly 35 to 38,000 miles per hour. Now, imagine something 3 times faster, a spacecraft capable of sustaining 100,000 miles per hour. That's generously fast by anything humans have actually built for sustained outer solar system cruise. At 100,000 miles per hour, the distance from Earth to Neptune, roughly 2.7 billion miles, takes about 27,000 hours, a little over 3 years. To the termination shock, at 8 to 9 billion miles, just over 10 years. To the heliopause, at 11 to 12 billion miles, 12 to 13 years. 12 or 13 years of continuous travel at 3 times our best sustained speed, just to reach the edge of the solar wind. And the Oort cloud still hasn't started. The inner edge of the Oort cloud is at 2,000 astronomical units, 186 billion miles. At 100,000 miles per hour, that's 1,860,000 hours. About 212 years. More than 2 centuries of continuous travel to reach the beginning of the Oort cloud. The outer edge, 100,000 astronomical units, is about 9.3 trillion miles away. At 100,000 miles per hour, reaching it requires about 9.3 billion hours. 1,060,000 years. over 1 million years of continuous travel. These are not approximations. They're not figures chosen for dramatic effect. They're the actual geometry of where we live, expressed in units of our best current engineering. The time it would take to cross our own solar system from the Sun to the outer Oort cloud at the fastest speed we've ever sustained is longer than our entire species has existed by a factor of several. The solar system is not large in the way that a continent is large, or even in the way that a planet is large, or a star system in the casual sense. It's large in a way that makes the concept of reaching its outer edge almost meaningless without propulsion that doesn't yet exist. Not improved versions of what we have. Not incremental engineering refinements. Something categorically, fundamentally different. A different energy source. A different exhaust velocity. A different relationship between propellant mass and achievable velocity. The outer solar system will wait for that technology. It has been waiting for 4.5 billion years. It is in absolutely no hurry. The gap between what we've built and what we'd need is enormous, but it isn't infinite. The history of propulsion is a history of step changes, not incremental improvements, but category shifts. From sailing ships to steam. From propeller aircraft to jet turbines. From chemical rockets to nuclear reactors in submarines. Each step opened distances that were previously unreachable in practical terms. The step from chemical rockets to fusion propulsion is larger than any of those. But the pattern holds. The question isn't whether propulsion adequate for the outer solar system is physically possible. It is, without question. The question is whether the civilization that builds it will still be interested in going. It's worth considering what the pace of development in the first century of spaceflight actually looked like. Because it's easy to treat the barriers to the outer solar system as permanent when they're more accurately described as currently prohibitive. In the 1920s, reaching orbit was science fiction. In 1957, something orbited Earth for the first time. In 1969, humans walked on the moon. In 1973, a spacecraft crossed the asteroid belt. In 1979, one flew past Jupiter. In 2012, one entered interstellar space. A trajectory from a 41-foot rocket hop in a New Mexico field to interstellar space in 86 years. The rate of expansion was remarkable. What hasn't kept pace is propulsion physics. Chemical rockets today are not fundamentally different from chemical rockets in 1960. The exhaust velocity ceiling set by chemistry hasn't moved. Breaking through it to nuclear, to fusion, to something capable of reaching the Oort cloud in decades requires advances in physics and engineering that may take generations. But those are engineering problems in domains that have barely been developed. The nuclear pulse propulsion concept was studied seriously in the 1950s and 60s, and then largely set aside for political and treaty reasons, not physical ones. Fusion propulsion has received far fewer resources than the problem warrants. The technologies exist as serious proposals backed by real physics. Whether they get the resources and urgency that the early space program received is a question about priorities, not physics. The cold at the edge of the solar system is not cold in any sense that everyday human experience prepares you for. Before thinking about the machinery, think about the physics of heat at those distances for a moment. Temperature is a measure of the average kinetic energy of particles. At absolute zero, particle motion stops entirely, as much as quantum mechanics allows, anyway. The cosmic microwave background, at 2.7 Kelvin, represents the residual thermal energy of the Big Bang, spread across the volume of the observable universe. Even in the most remote regions of intergalactic space, far from any star or galaxy, a body eventually thermalizes to this background and doesn't cool further. The Oort cloud, sitting within the gravitational domain of a star, at distances where the Sun contributes almost nothing to the thermal budget, approaches but doesn't quite reach this cosmic floor. Perhaps 3 to 7 Kelvin, depending on location. That's the thermal environment any mission to the outer solar system faces. The coldest temperature ever reliably recorded at Earth's surface was about -129 degrees Fahrenheit at the Soviet Vostok station in Antarctica in 1983. That temperature is dramatically warm compared to the outer Oort cloud. The universe has a baseline temperature set by the cosmic microwave background radiation, the residual thermal glow of the Big Bang, stretched and cooled by 13.8 billion years of cosmic expansion to an almost, but not quite, zero temperature. That baseline is 2.7 Kelvin, 2.7 degrees above absolute zero, -455 degrees Fahrenheit. Absolute zero is the theoretical lower limit of temperature, the point at which all thermal motion of particles ceases. It cannot be reached in practice, but it can be approached arbitrarily closely. The cosmic microwave background sets the floor at 2.7 Kelvin, because even in the emptiest regions of space, a body radiating energy will always absorb radiation from the cosmic background and reach thermal equilibrium at that temperature rather than cooling to absolute zero. In the Oort cloud, the Sun contributes essentially nothing to the thermal environment. At 2,000 astronomical units, the Sun's radiation is reduced to 1/4 of its intensity at Earth. The objects of the inner Oort cloud sit at temperatures of perhaps 5 to 7 Kelvin. At the outer edge, closer to 3 Kelvin, within a few degrees of the cosmic floor. For machinery operating in that environment, these temperatures are catastrophic without active preparation. Electronics have minimum operating temperature ratings. Below certain temperatures, semiconductor behavior changes in ways that cause systems to fail. Transistors stop switching reliably. Memory cells lose stored data. Processors produce incorrect results or halt entirely. These aren't just inconveniences. They're fundamental failures of the computing systems that would control a spacecraft. Beyond electronics, the mechanical environment at cryogenic temperatures is brutal. Metals contract. Different metals contract at different rates, which means joints and structural connections built with dissimilar materials experience stresses as temperatures drop, stresses that can crack joints, rupture seals, or shear fasteners. Elastomers that provide seals in fluid systems harden. Below certain temperatures, they become rigid and crack under any mechanical stress. A cracked seal in a pressurized system means a leak. Lubricants that flow freely at normal temperatures thicken, then gel, then solidify. Any moving mechanical component dependent on fluid lubrication can seize. A stuck valve, a frozen actuator, a deployment mechanism that won't open. Any of these could end a mission. The engineering response to this environment is active heating using electrical power. Radioisotope heating units, small cylinders containing radioactive material that generates warmth through natural decay, have been standard equipment on outer solar system missions for exactly this reason. For a crewed spacecraft in the Oort cloud, the heating demand is much larger. The human body generates heat through metabolism, but it also requires external warmth to maintain core temperature. The crew compartment must be actively maintained at habitable temperatures, roughly 60 to perhaps 80 degrees Fahrenheit, against an exterior environment at -400, 52 to -455 degrees Fahrenheit. The temperature difference is over 500 degrees. Insulation can reduce the rate of heat loss dramatically. It cannot reduce it to zero. Active heating must continuously compensate for what leaks through the best insulation buildable. If the power systems supplying that heat fail, the interior temperature falls. In an environment that cold, there is no gradual, forgiving decline that gives a crew hours to troubleshoot. A thermal management failure at those distances is an immediate crisis, solvable only with what's aboard, because any response from Earth arrives months later. The temperature challenge for biological systems is worth understanding in more physical detail than it usually receives. The human body maintains its core temperature at about 98.6 degrees Fahrenheit. It does this through metabolic heat generation. The chemical reactions of cellular respiration produce heat as a byproduct, and that heat keeps the body's biochemistry operating in its functional range. But the body is not a perfect insulator. It loses heat continuously to its surroundings through conduction, convection, and radiation. On Earth, the environment, air, ground, sunlight prevents the body from losing heat faster than it generates it. In a spacecraft in the Oort cloud, the exterior is at -452 to -455 degrees Fahrenheit. Nothing external is providing heat. Everything is receiving it. The spacecraft's hull radiates heat outward into the void continuously. Insulation slows this. It doesn't stop it. Active electrical heating must continuously supply the heat the hull continuously loses. The power requirement to maintain a habitable interior temperature in that environment is substantial. And the consequences of heating power loss are severe on a timescale determined by the spacecraft's thermal mass and insulation performance. With excellent insulation, a complete heating failure might give a crew several hours before interior temperatures approach the danger threshold. With less insulation, faster. This is an argument for redundant power systems, designed with the seriousness that the consequence demands. Every critical thermal management system needs backup. Every backup needs its own backup. The engineering philosophy for a crewed Oort cloud mission would need to be more conservative than any crewed mission ever attempted. The radiation environment in the outer solar system and beyond the heliopause is one of the least discussed hazards of any deep space mission, possibly because it's invisible, chronic, and statistically expressed rather than acute and dramatic. Inside the heliosphere, particularly in the inner solar system near Earth and Mars, the dominant radiation concern for any crewed mission is solar in origin. Solar energetic particle events, sudden bursts of high-energy protons and electrons released during solar flares and coronal mass ejections, can deliver doses dangerous to an unshielded crew in hours. These events are sporadic, partly correlated with the solar cycle and partially predictable. Space weather monitoring provides some warning. Mission timing can reduce exposure during periods of heightened solar activity. Spacecraft design can include storm shelters, regions with additional mass to hide behind during the worst events. Running in parallel with the acute solar threat is the chronic background of galactic cosmic rays. These are atomic nuclei, protons, helium nuclei, and a smaller fraction of heavier elements, including carbon, oxygen, silicon, and iron, that have been accelerated to fractions of the speed of light by supernovae, pulsar wind nebulae, and the turbulent magnetic fields woven through the galaxy. The most energetic galactic cosmic rays carry energies many orders of magnitude beyond anything the most powerful particle accelerators humans have ever built can achieve. Inside the heliosphere, the Sun's extended magnetic field partially deflects galactic cosmic rays. This is called solar modulation. It's measurable. The galactic cosmic ray intensity at Earth is noticeably lower during solar maximum, when the heliospheric magnetic field is stronger and more organized, than during solar minimum. Moving outward through the heliosphere, solar modulation weakens progressively. At the termination shock, the particle environment changes measurably. In the heliosheath, complex particle dynamics modify the cosmic ray spectrum in ways that are still being fully characterized. Beyond the heliopause, solar modulation is gone. Galactic cosmic rays arrive at their full, unmodified interstellar intensity. Nothing stands between a spacecraft and the full particle radiation environment of the galaxy. For a crew spending years in that environment, the accumulated radiation dose is substantial by any measure used in space medicine. But the numbers alone don't fully capture the concern. Galactic cosmic rays include a component of heavy, high-energy nuclei, iron nuclei, moving at a significant fraction of the speed of light, are a frequently cited example that produce qualitatively different biological damage from conventional radiation types. A single heavy nucleus passing through biological tissue creates a dense track of ionization along its path. The chemical damage in that track, broken DNA strands, disrupted cellular machinery, reactive oxygen species generated in a dense column, is qualitatively different from the scattered ionization produced by X-rays or gamma rays. The density of damage along a single heavy particle track is high enough that the cell's normal repair mechanisms, which evolved to handle more diffuse damage, can be overwhelmed or can introduce errors when attempting to repair it. Studies with animals exposed to simulated high-charge, high-energy cosmic ray particles at accelerator facilities where beams of iron or silicon nuclei can be directed at biological samples have found effects on the central nervous system that appear specific to this type of radiation. Changes in spatial memory, changes in decision-making and risk assessment, cognitive effects that don't follow the simple dose-response relationship of conventional radiation, and that appear at dose levels lower than those expected to cause traditional radiation. Sickness. The mechanisms are being investigated. The implications for crews exposed to the interstellar cosmic ray background for years are not fully characterized. This is a known unknown. We know there's likely a problem here. We know it matters, and we don't yet have complete enough data to precisely quantify it. Shielding helps imperfectly. The most energetic galactic cosmic rays penetrate meters of any material. No practical spacecraft wall is meters thick. The best commonly proposed strategy for the lower energy fraction of the spectrum is water. Hydrogen atoms in water are effective at absorbing energy from fast protons without generating cascades of secondary particles, which dense materials like steel tend to produce when hit by high-energy cosmic rays, making the radiation environment inside a well-shielded steel hull potentially worse than inside a less shielded one for certain particle energies. Surrounding the crew compartment with water tanks serves the dual purposes of radiation shielding and water supply. It's not a complete solution, but it's a practical step. Every shielding decision involves trade-offs between protection level, mass, and the downstream consequences of adding mass to a spacecraft. Every kilogram of shielding is a kilogram that requires more energy to accelerate and decelerate. More energy means more fuel. More fuel means more mass. The mass budget of any space mission is a tight constraint, and radiation shielding competes with everything else for it. The honest answer is that there is no design that eliminates the risk. There's a design that reduces it to what the crew and the mission planners agree is acceptable. And for a mission to the deep outer solar system, years in the full galactic cosmic ray environment, the residual risk, even with good shielding, is not trivial. There's also the longer-term question of what chronic, multi-year exposure to the galactic cosmic ray environment does to the cardiovascular system. This is an area of space medicine research that has accelerated as long-duration Mars missions have moved from theoretical to actively planned. Studies with rodents exposed to simulated galactic cosmic ray beams have found not just elevated cancer risk, but evidence of accelerated cardiovascular disease. Oxidative stress in arterial walls from ionizing radiation, inflammation, changes in arterial composition resembling early atherosclerosis. The heart and blood vessels aren't usually the first organs thought of in radiation protection discussions. But for very long exposures to high-energy particle radiation, cardiovascular effects may be as clinically significant as cancer risk. The data is primarily from animal studies, and extrapolation to human physiology carries uncertainties. But the signal is there, and space medicine researchers take it seriously. For a crew spending years in interstellar cosmic ray conditions, cardiovascular monitoring would need to be a central part of the mission health program. Exercise regimens already essential for preventing bone density and muscle mass losses from microgravity would also need to account for cardiovascular health in an elevated radiation environment. The challenge of keeping a crew healthy for years in the outer solar system involves not just radiation, biology, but nutrition, psychology, microgravity, physiology, and cardiovascular health simultaneously, in a regime where no previous mission provides directly applicable experience. The communication constraint is absolute in a way that no amount of technological progress can change. Radio signals travel at the speed of light. The speed of light is the maximum speed at which information can travel. Everything we understand about physics says nothing exceeds it. Improving radio technology, using more powerful transmitters, using better receivers, using laser communication instead of radio. None of this changes the fundamental constraint. Information travels at the speed of light, no faster. At 1 astronomical unit from the Sun-Earth's distance, a signal takes about 8 minutes and 20 seconds to arrive. At Neptune's orbit, 30 astronomical units, about 4 hours and 10 minutes each way. A single question and answer exchange takes over 8 hours. If something goes wrong and a crew asks for advice, the answer arrives 8 hours after they sent the question. In those 8 hours, the situation has either been resolved or it hasn't. Earth's advice arrives after the outcome. At the heliopause, 100 to 125 astronomical units, signals take 13 to 17 hours each way. A round-trip exchange takes over a day. at 1,000 astronomical units, 5 to 6 days each way. 11 to 12 days for one back and forth. At the inner Oort cloud, 2,000 astronomical units, 11.5 days each way. 23 days for one question and answer. At 10,000 astronomical units, 57 days each way. About 4 months for one exchange. Whatever emergency develops at 10,000 astronomical units, a medical crisis, a system failure, a navigation problem, the crew handles it. Completely. With what they have. Because by the time Earth receives the distress call and responds, roughly 4 months have passed. The situation resolved itself months ago, one way or the other. Mission control exists for a crew at 10,000 astronomical units, the way a friend in another country exists when you're having a heart attack. They care. They're there. They cannot help in any practical, timely sense. The most isolated human beings in the history of Earth have been far less isolated than this. Antarctic winter overcrews at the South Pole are isolated for months at a time. They can communicate in real time. Submarine crews on extended patrols maintain communication. Sailors crossing oceans alone had no radio, but they knew what was waiting for them on the other side. A crew at 5,000 astronomical units from Earth is in a category of isolation that has no historical precedent. Not approximately without precedent. Without precedent in any meaningful sense. The psychological implications of this are serious and not fully understood. Humans are social animals in a way that runs deeper than preference. The need for social connection, for real-time feedback from other people, for the knowledge that the world continues and others are in it with you, is not a luxury. It's a psychological necessity that, if unmet over long periods, produces measurable effects. Loneliness is associated with elevated stress hormones, disrupted immune function, sleep disruption, cognitive impairment, and elevated risk of a range of health conditions. These effects scale with the depth and duration of isolation. A crew in the Oort cloud can communicate with each other. They have their small group. But their connection to the rest of humanity is a signal that takes months to arrive. The Earth, they knew when they left, is months out of date in every message they receive. Events happen. People they knew get older, have children. Some of them will be gone. The world changes. And the crew receives information about those changes months after the fact. This is its own kind of isolation, not physical, but temporal, cut off from the present by the speed of light. The selection of the crew for such a mission, and the ongoing psychological support of that crew once underway, would be among the most demanding challenges of any outer solar system program. More demanding than most of the hardware engineering, possibly. Hardware can be tested until the failure modes are mapped. The psychology of small groups under extreme isolation for years cannot be fully simulated on the ground in a way that translates reliably. What would you actually see? The honest answer involves both more and less than most depictions suggest. In space, away from any atmosphere, the stars are steady, not twinkling. Earth's atmosphere refracts. Starlight bends it slightly as the starlight passes through pockets of air at different temperatures, and this refraction flickers as the air moves. In space, there's no air. Every star is a precise, unwavering, mathematical point. No twinkle. No distortion. Just clean, exact points of light in a black sky. The number of stars visible is greater than from any location on Earth's surface, because the atmosphere absorbs a fraction of incoming light, even on the clearest nights. In space, every photon a star emits in your direction arrives at your eye. The sky is richer, and it's also completely silent. The silence is worth dwelling on. On Earth, even in the most remote location, there is always some background noise: wind, insects, distant water, the subtle creaking of the ground. In space, there is no medium for sound to travel through. There is nothing. Whatever happens outside the spacecraft hull, whatever collision, whatever burst of particle radiation, whatever change in the environment arrives silently. The universe is operating at full scale around the spacecraft, and none of it makes a sound. There's no sound in space. Not atmospheric noise. Not wind. Not the subliminal background of a living world. Nothing. The stars burn in absolute silence, and they have been doing so for billions of years while nothing has been watching. Moving outward through the solar system, the sun changes character completely. At Earth, it's impossible to look at without eye protection. It dominates the sky. At Mars, it's clearly smaller than from Earth, but still the overwhelming source of light. At Jupiter, it's a brilliant disk, about 1/25 the apparent diameter it has from Earth. Still a disk. Still obviously the Sun. At Saturn, it's about 1/90 the apparent diameter. Very bright, but smaller than you might expect. At Uranus, the apparent diameter is down to about 1/350th of what it is from Earth. A very bright point source to the naked eye. At Neptune, it looks like a very bright star. No disk visible without optical aid. It's still dramatically brighter than any actual star in the sky. The difference in brightness between the Sun from Neptune and the next brightest star in the sky is still orders of magnitude. But it has lost its character as the Sun. It's become a very bright star. Further out, into the Kuiper belt, across the heliosheath, toward the heliopause, it diminishes further. At 1,000 astronomical units, the Sun is no longer obviously dominant to the naked eye. It's a very bright star in whatever constellation it happens to be near from that vantage. Without specific knowledge of which point to look for, you might scan the sky for a moment before locating it. At 10,000 astronomical units, the Sun is one of the brightest stars in the sky. Not the brightest, not obviously distinguishable from Sirius or Canopus or Alpha Centauri just by looking. You'd need to know where to look. And when you find it, when you know which ordinary-looking star in the ordinary-looking sky is the Sun, you understand something about scale that no diagram communicates. That point of light is where Earth is, where every human who ever lived was born, where all of human history took place, where everything you've ever known is located. A point of light. In exchange for the Sun's prominence, there's the Milky Way in full. Not the pale, soft band visible from dark Earth sites. The full structure. The galactic plane blazing in hundreds of billions of stars. The dense, bright core region towards Sagittarius, partially obscured by dust clouds but still luminous. The dark lanes of absorbing dust cutting through the bright background, their shapes changing slowly as you move to a new vantage point outside the heliosphere. Individual nebulae visible as patches of color, emission nebulae glowing in reds and pinks, that Earth's atmosphere partially absorbs, and that even the best ground-based images can't fully capture in naked eye viewing. Globular clusters, standing out as dense, spherical concentrations of hundreds of thousands of stars, each resolved individually in the densest regions. Open clusters scattered through the arms. The Andromeda Galaxy, visible as a vast elliptical structure spanning several degrees of sky. The large and small Magellanic Clouds, visible in the southern sky as distinct, separate structures. The visual richness of the universe, completely unobscured, from a vantage point outside the solar wind. No human eye has ever seen it from that vantage, and you'd be under it in total isolation, surrounded in every direction by the void. The spacecraft, the crew, and the stars. The loneliness would be unlike anything humanity has yet put a proper name to. Navigation in the outer solar system is worth understanding as its own challenge, because the practical reality differs from intuition shaped by inner solar system missions. In the inner solar system, navigation combines star tracking, Earth-based ranging signals, and gravitational modeling. Mission controllers send signals to a spacecraft, measure the round-trip travel time to determine distance, measure the Doppler shift of the return signal to determine the radial velocity component, and combine these measurements with trajectory models to compute the spacecraft's position precisely. For a spacecraft at 10,000 astronomical units, the round-trip ranging signal takes about 57 days. Position determination is still possible in principle, but the slowness of the communication means that any trajectory correction is planned, executed, and confirmed over timescales of months. A navigational error identified from Earth data takes months to confirm and months more to correct. Any crew at those distances must be capable of autonomous navigation at a level no crewed mission has required. Onboard star trackers. Compute orientation from stellar positions. This works anywhere in the solar system. Position in 3 dimensions relative to the Sun requires onboard ranging, combined with extremely precise accelerometers tracking every velocity change from every thruster firing. The technology for this exists in concept. Building it to the precision required for Oort cloud navigation and validating it for multi-year operation without maintenance or update hasn't been done. It's another engineering problem in the very long list of engineering problems that a crewed outer solar system mission represents in full. Not impossible, just not built. The scientific reasons for eventually reaching the outer solar system are not abstract. They address fundamental questions about where we came from, what environment we live in, and what the long-term future of life on Earth might look like. The icy bodies of the Kuiper Belt and Oort cloud are 4.5 billion-year-old chemical records of conditions in the early solar nebula. The inner solar system has been processed repeatedly. Rocky planets have been melted in their formation, differentiated heavy elements sinking to the core, lighter elements rising geologically reworked by tectonics and volcanism, and reset repeatedly by large impacts. Whatever primordial chemistry they carried from the solar system's formation has been largely overwritten by 4.5 billion years of geological activity. The outer solar system objects have experienced almost none of this. Sitting at temperatures within a few degrees of absolute zero, in the absence of liquid water, exposed only to a very low level of radiation, they have been chemically inert since their formation. Their compositions reflect conditions in the protoplanetary disk at different distances from the young sun, different temperatures, different pressures, different chemical environments. Reading that record tells us things about the solar system's origins that no inner solar system sample can. The water question is central. Earth formed in the inner solar system, in the region where temperatures during planetary formation were high enough that water ice couldn't condense. The rock that accumulated to form Earth was dry. The water in Earth's oceans came from somewhere else. The most widely supported current hypothesis is delivery by icy impactors, objects from the outer solar system that struck the early Earth and delivered water along with other volatiles. The primary evidence used to trace the source of Earth's water is the ratio of deuterium-heavy hydrogen to ordinary hydrogen in Earth's ocean water. Different populations of solar system objects have different deuterium to hydrogen ratios, reflecting conditions at the locations and temperatures where they formed. Some classes of asteroids match Earth's ocean-water ratio well. Some comets match. Others don't. The story is complicated. Getting samples of pristine Oort cloud material ice that has never been heated by the sun, never been processed by repeated perihelion passes, would provide the most direct access to the original outer solar system water reservoir. The question of how organic molecules reached the early Earth is connected. Amino acids have been found in carbonaceous meteorites. Glycine, one of the simplest amino acids, was detected in material returned from Comet Wild 2 by the Stardust mission. Complex organic molecules, including molecules that are biologically relevant, exist in outer solar system material. Long-chain organic compounds have been found in interstellar space through radio astronomy. The chemical inventory of the early solar system, preserved in Oort cloud objects, represents the starting material from which Earth's chemistry, including, eventually, life, emerged. Understanding what that starting material actually contained, in detail, is fundamental to understanding how life arose on Earth. The interstellar medium, just beyond the heliopause, carries information we can't access from inside it. The properties of the local interstellar gas, its density, temperature, composition, ionization state, magnetic field, strength, and orientation determine the shape and properties of the heliosphere. The heliosphere acts as a partial shield against galactic cosmic rays, as already discussed. But the degree of shielding depends on the properties of the interstellar medium pressing on the heliosphere from outside. If the local interstellar medium becomes denser, as can happen when the solar system passes through a dense interstellar cloud on its galactic orbit, the heliosphere compresses. A compressed heliosphere provides less shielding. Galactic cosmic ray flux inside the solar system increases. How this has varied over the history of the solar system, and what consequences it may have had for Earth's climate and biology, requires knowing the history of the solar system's path through the galaxy and the interstellar medium it has traversed. Measurements from spacecraft that can directly sample the interstellar medium over time in multiple directions would dramatically improve our understanding of this. The outer solar system is also where the dynamical history of the solar system is written most clearly. The Oort cloud's existence is itself a prediction of planetary formation models. When the giant planets formed and migrated, they scattered billions of planetesimals, the building blocks of planets, outward. Some were ejected from the solar system entirely. Others landed in the Oort cloud, their orbits slowly rounded by the gentle perturbations of passing stars and the galactic tide over billions of years. The Oort cloud is what survived, a fossil of the solar system's early dynamical violence, preserved in cold storage ever since. The current orbital architecture of the planets, the Kuiper Belt, and the Oort cloud reflects events in the solar system's first 100 million years, when the giant planets were migrating and interacting with each other and with the disk of material surrounding them. Models of this early dynamical history make predictions about the outer solar system's structure that can be tested with better observations and in situ measurements. The Oort cloud's existence and properties are themselves a record of the Sun's early stellar environment. The Sun formed in a cluster of stars. As the cluster dispersed, passing stars and the tidal forces of the cluster shaped the outer solar system into the configuration we observe. Understanding that configuration in detail is, in part, reading the record of where the Sun came from. And the outer solar system will surprise us. It always has. Every time observational reach has been extended from the inner Kuiper belt to the scattered disk to Sedna-class objects, something was found that the existing models didn't predict. Whatever we find in the Oort cloud will not simply confirm what we expect. It never does. The solar system has a long track record of being more surprising than the people studying it expected. There's no reason that trend stops at the heliopause. The propulsion problem deserves direct treatment. Because no amount of mission, architecture, or crew selection matters if you can't get a spacecraft to the outer solar system on a timescale that's relevant to human lifespans. Chemical rockets burn propellant in combustion reactions. The energy available is determined by chemistry, specifically by the bond energies of the reactant molecules. The exhaust velocity of the combustion products, the key figure that determines how efficiently a rocket converts propellant into velocity change, is set by the temperature and molecular weight of those exhaust products. For the best chemical combination available, liquid hydrogen and liquid oxygen, the specific impulse tops out at around 450 seconds. This corresponds to an exhaust velocity of about 2.9 miles per second. No chemical rocket can do dramatically better than this. The chemistry has a ceiling. The rocket equation derived by Konstantin Tsiolkovsky in 1897 is not a design limitation that engineering can circumvent. It's a mathematical description of conservation of momentum. To achieve a given change in velocity with a rocket that has a given exhaust velocity, you need a specific ratio of propellant mass to final mass. For high delta-V missions that require very large changes in velocity, the required propellant-to-payload ratio becomes extremely large very quickly. For a mission requiring velocities that could reach the Oort cloud in decades rather than centuries, the propellant mass required with chemical rockets would exceed the payload mass by factors that make the mission impractical. Nuclear thermal propulsion uses a nuclear reactor to heat a propellant, usually liquid hydrogen, to much higher temperatures than chemical combustion achieves. Higher exhaust temperature means higher exhaust velocity. The specific impulse of nuclear thermal engines in the designs studied through the NERVA program in the 1960s and 70s reached around 800 to 900 seconds, about double the best chemical engines. Better. Still not adequate for reaching the Oort cloud in a human lifetime. Nuclear pulse propulsion is energetically more serious. The concept, studied as Project Orion in the late 1950s and 1960s, involved detonating nuclear explosive devices behind a massive pusher plate, separated from the main spacecraft body by a system of shock absorbers. The pressure pulse from each detonation accelerates the pusher plate, which transmits the impulse to the spacecraft through the shock absorbers. Thousands of detonations, at a rate of roughly 1 per second. Orion designs, studied by Freeman Dyson and others in the late 1950s, suggested that large Orion vehicles could achieve exhaust velocities equivalent to specific impulses of several thousand to branes, tens of thousands of seconds. This would allow cruise speeds of several % of the speed of light for large enough designs. At a few % of the speed of light, the inner Oort cloud becomes reachable in decades rather than centuries. The engineering challenges are severe. The pusher plate must withstand repeated nuclear detonations at close range without failing. The shock absorber system must preserve the rest of the spacecraft from the impulse. Crew, shielding from the radiation of each detonation, must be adequate. The detonation mechanism must be reliable for thousands of firings. The political and legal obstacles the Partial Nuclear Test Ban Treaty of 1963 prohibits nuclear explosions in space are also substantial. No Orion vehicle has been built. Ion drives achieve high specific impulse through electrical acceleration of ions. Specific impulses of several thousand seconds are achievable with current technology. The trade-off is thrust. Ion drives produce very small force. Tiny thrust means very slow acceleration. For a massive crewed spacecraft, the thrust-to-weight ratio of a practical ion drive is so low that the acceleration timescales become impractical. Fusion propulsion is the next significant step that physics plausibly allows. Fusion reactions combining light nuclei, typically deuterium and helium-3, or deuterium and tritium release energy per unit mass far beyond fission. Fusion rocket designs that have been analyzed suggest specific impulses in the range of 10,000 to 1,000,000 seconds, depending on the design and the degree of energy utilization. At those exhaust velocities, velocities of several percent of the speed of light become achievable with realistic propellant masses. The engineering problems are enormous. Controlled nuclear fusion has been an active research pursuit for over 70 years. Commercial fusion power plants, reactors that produce more energy than they consume, are not yet operating. The gap between a power plant fusion reactor and a compact fusion rocket engine, suitable for space, is itself enormous. The timescale for fusion propulsion, capable of reaching the Oort cloud in decades, is measured in generations, not years. Antimatter propulsion sits at the theoretical maximum. Matter-antimatter annihilation converts mass entirely to energy, governed by E equals mc squared. 1 gram of matter and 1 gram of antimatter, annihilating completely, release energy equivalent to roughly 21.5 kilotons. No reaction releases more energy per unit mass. An antimatter rocket, capable of converting annihilation energy efficiently to thrust, could achieve exhaust velocities approaching the speed of light. The production problem makes it currently fantastical. All the particle accelerators on Earth, running continuously for thousands of years, would produce micrograms of antimatter, enough for nothing. The storage problem is equally severe. Antimatter must be kept isolated from ordinary matter in magnetic or electric containment systems that cannot fail, ever. These barriers are real, but none of them are forbidden by physics. They're engineering problems in a domain that hasn't been seriously developed. The history of human technology is full of problems that were once described as permanently prohibitive that are now routine. None of this means the Oort cloud becomes accessible next decade. It means it's not inaccessible in principle. The distinction matters. There's also a propulsion concept that occupies a completely different part of the design space from all of the above, the laser sail. Build an enormous array of lasers, either on the ground or in space. Focus their combined output onto a very lightweight, highly reflective sail attached to a spacecraft. Radiation pressure from the laser beam accelerates the sail. The energy source stays behind. The spacecraft carries no propellant at all. This is the key point. The rocket equation places a fundamental limit on propellant-driven spacecraft. A laser sail sidesteps the rocket equation entirely. The Breakthrough Starshot initiative has proposed this approach for sending tiny probes to Alpha Centauri, gram-scale spacecraft, accelerated to a significant fraction of the speed of light by a sun-time, ground-based laser array. For the Oort cloud, which doesn't require nearly as much velocity as an interstellar trip, the laser array requirements are correspondingly less extreme. The engineering is still formidable. Keeping a focused beam on a rapidly moving sail over millions of miles requires extraordinary beam control. For a crewed spacecraft, much heavier than a gram-scale probe, the required laser power scales dramatically. The deceleration problem is also entirely unsolved. A laser sail can be accelerated by a laser array at the origin, but decelerating at the destination requires either another laser array at the destination or a different mechanism entirely. Arriving at the Oort cloud at high speed without a way to slow down produces a very brief mission. But the physics of laser sails is sound. The energy source is external. The spacecraft mass can be minimized. The concept addresses the rocket equation from a completely different angle than every other propulsion type that came before it. Every time humanity has extended its observational reach outward with better telescopes, with spacecraft that traveled farther, with instruments sensitive to different things, the solar system has returned surprises. Every single time, without exception. Not incremental refinements of existing models. Not the kind where the model was right and the details were wrong. Surprises where fundamental assumptions were overturned. Repeatedly. At every distance we'd never looked before. The outer solar system wasn't supposed to have active geology. Pluto wasn't supposed to have active geology. Enceladus wasn't supposed to have a subsurface ocean with hydrothermal vents. Europa's ocean was expected, but its depth and the evidence for active hydrothermal circulation were not. Titan's surface weather and river systems weren't the expected outcome. And there's no reason to think the pattern stops at the Oort cloud. Sedna's orbit had no place in the models of the outer solar system as it was understood when Sedna was found. The models had to change. They always do. The pattern is consistent enough to constitute its own kind of evidence. Whatever is in the Oort cloud, whatever exists in the interstellar medium just beyond the heliopause, in the regions no instrument has reached, in the volumes of space that no mission has yet traversed, it will not simply match the predictions made from inside the heliosphere. It will change them. That's not a problem. That's not a complication. That's the nature of exploration. It has always been the nature of exploration. Discovery advances at the boundary between what's known and what isn't. The Oort cloud is as far toward the unknown as you can get, while still technically being inside the same solar system. The solar system isn't just the region we've explored. It's the region we're capable, in principle, of eventually exploring. All of it. Including the parts that would take 1,000,000 years at our current best speed. And everything we've ever sent into space has barely scratched the surface of it. The distance is unlike anything humanity has ever traversed. The cold approaches the absolute minimum temperature the universe allows. The isolation would be a new category of human experience, not an extreme version of existing isolation. The radiation would be constant, invisible, and accumulating. The communication delay would turn Earth from a home into a correspondent whose letters take months. The most distant human-made objects are roughly 120 to 130 astronomical units from the Sun, a fraction of 1% of the distance to the Oort cloud's inner edge. The Oort cloud's 2 trillion objects are our nearest neighbors in the solar sense. We just haven't reached any of them yet. We've reached interstellar space, in the sense of the solar wind boundary. We haven't begun to cross our own solar system, in the gravitational sense. Those are 2 very different things, separated by nearly 2,000 astronomical units of empty space between the heliopause and the Oort cloud's inner edge. No law of nature prevents the development of propulsion adequate for the task. The barriers are technological and economic and political. They're real barriers. They may not be overcome for a very long time, but they're not permanent. Nothing about the physics requires them to be. The same species that went from the first powered flight 12 seconds, 120 feet, to landing on the moon in 66 years, is capable, in principle, of the engineering leaps required for the outer solar system. We are not there. We are not close to being there. But the arc of human technological development doesn't suggest a permanent ceiling below the Oort cloud. The Oort cloud has been there for 4.5 billion years. It will wait. That's one thing about a boundary defined by the slow fading of gravity into the galaxy. It is genuinely not going anywhere. Neither is any of the rest of it. The solar system is not what most people think it is when they picture it. It's not 8 planets in a tidy diagram around a moderate star. It's a gravitational empire extending nearly halfway to the nearest star, containing 2 trillion frozen remnants of its own formation, bounded not by any planet's orbit or by any spacecraft we've launched, but by the slow fading of one ordinary star's gravity into the immensity of the galaxy. We live at the center of it. We always have. We just haven't looked far enough outward to understand the full scale of what surrounds us. The planets we know, Mercury to Neptune, occupy the innermost region of the solar system's actual territory. Beyond the last planet, there is vastly more than anyone typically accounts for. Cold and dark and invisible, full of the most ancient, preserved material in the solar system. Full of comets that will light up Earth's sky thousands of years from now. Full of the record of where the solar system came from and what it was originally made of. Full of answers to questions we're only beginning to form, precisely enough to ask. The terrifying journey to its edge is also, if you shift your perspective by just a fraction, something else. It's a measure of the kind of universe we live in. A universe where even one ordinary star in the outer arm of a spiral galaxy among 2 trillion galaxies commands a gravitational domain so enormous that the fastest thing humanity has ever built would require 1 million years to cross it. A universe where most of our own solar system still remains completely unexplored. A universe where discovery, at every scale, in every direction, and at every distance we haven't yet reached, is still waiting. Good night.